Hello everyone, I am Ricardo, and I'm a software engineering intern here at Google. I'll be presenting today with Easwar some work that has been going on in gRPC-Go. In essence, this presentation is how we can maximize the memory usage inside of gRPC-Go. But first, before we can actually talk about the work that we've been doing, I want to go through some concepts related to gRPC-Go. So first, gRPC and protobufs are as thick as thieves, right? In protobufs is where you define how your service is going to look, what sort of messages you're going to send, and what are the RPCs that you're going to support. In the case of gRPC-Go, HTTP2 is a protocol that we use for the basis of networking. So everything in gRPC goes through HTTP2 in the wire. Finally, it is worth mentioning that there are multiple components involved in every message inside of gRPC-Go. And today we're going to talk about some of them. But before we can deep dive into these components, I want to go through some of the motivations that were behind the work that we've done so far. And so the main motivation for this effort was a performance issue on huge proto messages. So when we were sending huge proto messages, we were seeing a lot of memory consumption. And so we did some profiling and some benchmarks on gRPC-Go to try to figure out why this was happening. And we basically figured out that there were two main problems with gRPC-Go, the number of copies and the number of allocations that were being made inside of the application. And so now that we investigated all of this, we came up with a plan to solve this. It is basically a two-part plan. Firstly, we would need to rethink the encoding API. And secondly, we would need to rework the transport. And so you might be thinking, what are these components? What are they used for? And how do we make them better? And so firstly, I'm going to give the stage to Easwar so he can talk about the encoding API.
Thanks, Ricardo. So what is encoding? So basically, at a very high level, encoding is converting your request or response messages, which are usually proto messages, into bytes that can be sent on the wire. And decoding is basically the opposite of that, where you get bytes from the wire and you have to convert them back into your proto messages. So at a very high level, let's see where encoding happens in gRPC. So you have your client application, and that's making an RPC. So this message is now given to the encoder. And the encoder comes back with a bunch of bytes, and they go through a lot of other gRPC stuff before they get put on the wire. And the same thing happens on the other side. Basically, you get bytes on the wire, it goes through a bunch of gRPC stuff, and then it goes through the decoder, which gives you back the proto message that can be passed to the server application. So the key takeaways here are that encoding is the first thing that happens on the send path, and decoding is probably the last thing that happens on the receive path. And the most commonly used encoding in gRPC is the protobuf encoding. In fact, in gRPC-Go, especially if you don't specify an encoding, we just default to the protobuf encoding. And so HTTP2 is basically the transport that is used by default, and it supports a header called content type, which basically specifies the nature of the data that's being sent in the request or the response message. So the value for that in gRPC requests and responses usually have this application/gRPC prefix, and it's suffixed by the actual encoding being used. So if you're using the protobuf encoding, then on the wire, the value for this header will be application/gRPC plus proto. Now, let's get to some caveats of the protobuf encoding. So up there, you see the unmarshal function, which is provided by the protobuf Golang library. And this has actually two major problems. The first one is that it takes a byte slice as input. It's a single flat byte slice, and it requires that the whole data that you want to deserialize is in a single contiguous buffer. For gRPC, where the actual request or response message goes as HTTP frames, it gets chunked into much smaller frames than your actual message size. So this means that gRPC needs to allocate a single buffer, put everything into that buffer, and then pass it to the unmarshal function, and this causes a lot of garbage. The second one is that it does not assume ownership of the input data. So basically what this means is, let's say that you have a big byte slice in your message, in your proto message. Like the unmarshaller actually ends up like allocating a new byte slice for it and copying over the data instead of like just pointing to it. Like both of these actually result in a lot of unwanted allocations and copies. So if you look at gRPC's encoding API, this very much resembles proto-marshal and unmarshal, and therefore it has the same problems of proto-marshal and unmarshal. Now let's actually go through the send and receive paths of an RPC message and see where we are incurring copies and allocations. So we start off with the application sending a message to gRPC, and gRPC gives that message to the codec. The codec comes back with bytes. So here we have a copy because the codec has to create that byte slice and put the serialized bytes into it. Next, gRPC hands off these bytes to the transport, and the transport has to hand off these bytes to the HTTP2 framer, which actually converts the bytes into HTTP2 frames. But before it does that, it has to allocate a small header, which is not the HTTP2 header, but it's a gRPC header. It's a 5-byte header, which is basically 1 byte saying whether the message is compressed or not, and 4 bytes indicating the length of the message. And because the framer API is such that it expects the whole data in a single byte slice, gRPC again has to make a copy and put the whole thing, like the header and the bytes, into 1 byte slice. Next, we have the framer passing it, like copying whatever bytes it gets into its own buffer. We'll see more about the problems in the framer, like Ricardo will talk about that in more detail. But all we need to know here is there's another copy there. And then the framer writes it to the network, and there's another copy there. So we have 4 copies on the send path. Similarly, on the receive path, you get bytes from the network. So this copy star is unavoidable because you need to copy bytes out of the network into your application space. And then it gets passed to the framer, and the framer has a buffer. So there is a copy there. And the framer gives it to the transport. And at this point, the transport has to make a copy because the framer has a single buffer. And like if the transport doesn't make a copy, the next call to the framer will actually override those bytes. Again, Ricardo will talk more about this. And then eventually gRPC gives it to the codec. There's another copy. And then finally, we get to the application. So here we've seen both the send and receive paths with a lot of unwanted copies. So at this point, we'll see how we addressed this issue. And we actually have Paul here from LinkedIn who did a bunch of work in this area, and a big thanks to him. So this is the package that Paul added. So we've called it the mem package, and it provides 3 major functionalities. The first one is the buffer. It's basically like a wrapped ref-counted byte slice. And it provides ways to get a reference, free a reference, and pass around the buffer without copies. And also it can be returned to a pool instead of just being garbage collected. The next one is a buffer slice, which is basically a slice of buffers or a collection of buffers. Because gRPC deals with a lot of chunk data, like buffer slices make a lot of sense. And this is basically the type that is passed around between components. And last but not the least is the buffer pool. It's basically a reusable pool of buffers. So instead of getting garbage collected, we put it back into the pool and reuse it. So this is how the encoding API v2 looks like. So basically, we have the same marshal and unmarshal functions, but instead of them taking a flat byte slice, they're now taking a mem.buffer slice. And we'll see some benchmarks. Do I have them here? Yeah, I introduced Paul before, but Paul will be happy to answer any questions at the end of the talk. So current status here is that Paul's PR has been merged, and it's been running for a while now in production in LinkedIn, and we are seeing like huge gains for large messages. We're also seeing a little bit of reduction for smaller messages. We're still investigating on ways to overcome that. And Ricardo has been doing a bunch of work, which once that gets merged, we hope to see even better performance. This is not very viewable from out there, but basically a before and after that we sort of tried to put in at the last moment. But we're happy to answer questions on it towards the end of the talk. That's mostly it from me, so I'll hand it back to Ricardo to talk about the work that he's been doing in the transport layer.
Thank you, Easwar. And so we're back to the transport. So first I want to go through what is a transport, right? And so the transport is an abstraction that, quoting what Easwar once told me when I was getting to learn all of this stuff, is what turns RPCs into a reality, right? And to me, it is what sits in between the wire and gRPC. So basically, the transport is in charge of managing all the HTTP2 semantics, so the rest of the application need not to know what is an HTTP2 stream or what is an HTTP2 frame, right? So the application can just send the message, and the transport will be in charge of encoding all the HTTP2 spec things that might be needed for you to properly go in the network. And so talking about the specifics of the transport, we're going to look at the HTTP2 framer. And so the transport has multiple components in charge of different things like flow control, stream management, amongst other things. However, my project revolved around the HTTP2 framer. And so the HTTP2 spec works by sending what we call frames, which are like the unit, like the most basic unit of communication in the HTTP2 spec. And so we call the piece of code that's in charge of making these frames the framer. And so these frames can convey information about the connection, about the server or the client, but mainly they're used for sending the data that we actually want to transmit through the network. And so we currently use the standard library that's provided by the Go HTTP2 experimental library. However, this work consisted in replacing this implementation with a custom one that fits our needs in gRPC. And so what were the main pain points that we had on the standard implementation of the framer? The first one was, as Easwar mentioned, they needed to materialize. And so what do I mean by this? If we look at the function signature that was provided by the HTTP2 framer, we see that it takes a single data slice. And so this meant that whenever we had like little pieces of the RPC message in different byte slices, we would need to create a buffer that was big enough to hold them both, and then copy that data into a single contiguous buffer so that we can actually call the API in the current framer. Another problem that we had was when reading data from the network. Easwar talked about it briefly, but basically the framer has this thing called frame invalidation. And so basically, it would read bytes from the network and then store them in a buffer inside of the framer. And we would get access to that data through a pointer to that buffer. So whenever the read frame happened again, that same buffer will be reused, and so the data will be rewritten. And this meant that the pointer that we had to the previous frame will be invalidated. And so the problem with this is that the time that we read the bytes from the transport is not the same that when we read the bytes into the framer. And so we needed to guarantee that the data will live long enough for it to be processed by other parts of the application. And so what ended up happening is that we needed to copy the data from the framer into a buffer that we can guarantee will live long enough. And finally, the other problem that the current implementation had was that we had this, wasn't the writing path. We have this optimization in the transport, which is called the buffer writer. So essentially, we don't want to do a lot of writes for small messages, because doing a write into a connection implies a syscall, and that can be expensive. So we have this buffer writer that basically batches up the small writes whenever we hit a certain quota, we then just flush that whole buffer. However, the way the framer works is by copying the data that you pass into it into its own buffer and then writing that data. So we were essentially having like redundant copies because we would have the data that we want to send through the network. We were copying it into the framer, and then the framer will be copying it again into our buffer writer. So we can avoid that copy thanks to our optimization there. And so that's I'm going to talk about how I solve each one of these problems. So first, we will take a scatter-gather approach for the API. And what do I mean by this? So we can leverage the new types introduced by the mem package. And so the new API, instead of taking a flat byte slice, it can take a buffer slice that has all these pointers to different buffers. And then we only actually write them to the buffer writer. On the other hand, for the reading validation, we will essentially now have a buffer pool so that we can read bytes from the network into the buffer from the buffer pool, and then give ownership of that buffer into the rest of the application. That way the application can keep that buffer for as long as it needs, and whenever it's done using it, it can return it to the pool for it to be reused by the framer again. And finally, the way we solve the last problem is by removing the buffering inside of the framer. So essentially, when we're writing data frame, instead of copying the data into a buffer that lives inside of the framer, we will just write that same data directly into our buffer writer. So that way we don't have like that redundancy in copies. And so for the execution of this project, we expect wins on CPU usage, as we are going to be mainly reducing the number of copies happening inside of gRPC. We will be able to give an option to opt out. So if we find any major bugs while the API stabilizes, we can switch back to the old framer. And finally, we still have benchmark spending as this work is ongoing. I still have a little bit more time left here at Google, and I'll be hopeful I can finish it before I leave. And so finally, if we take all that we've talked about today and we put it together in a single diagram, we can take back what Easwar was talking about when the sending path. And as we can see, we've reduced all the copies, as now we don't need to copy into the codec. We don't need to copy out of the codec since we have the new mem package. We don't need to copy for we to pass the data into the framer. And the only copy that remains is on the buffer writer, which is this like optimizations that we have for batching up writes into the network. So that one we still have. And it's the same for the receive path, in which now we don't have to copy except from when reading from the network, as we can now just use all these new data types that we've introduced to handle the ref counting and the pointers to the buffers. And so that's pretty much everything on our side. Thank you for listening to me. Does anybody have any questions? Yeah.
First of all, it was a great talk. Thank you very much.
Thank you.
Hi. So, if you use the buffer slice, didn't you you had loose coupling before that between the framing and the higher level buffers, and now, to me, it looks like we lump together a bunch of stuff. So we're like mixing different levels of abstraction within the buffer. I'm wondering if you could expand on that, like how is it implemented under the hood, and how do you maintain the pointers and make it efficient yet loosely coupled in terms of software design?
Do you want
that
a mic?
makes sense.
Can we have one of the other mics? Blue one?
Yeah, so basically the way that the buffer slice itself works is that it exposes a bunch of APIs that make it look contiguous. So you used to get just a byte slice, now you get a buffer slice, but as far as the way that you interact with it, it behaves functionally just like a normal buffer slice, number byte slice. So the only thing that in most cases, most applications won't manually like ref them or free them, right? It's only if you've got like really high performance setups, and the default like protobuf encoder will be taking care of that for you. But so in a scenario where you really have a custom use case where you want to make sure that you're reusing the memory as much as possible, or basically your message type is often like referencing big underlying byte slices, you're really just going to use the buffer slice API pretty much itself directly. Like you're not going to be managing that. So under the hood, it does itself try to like keep all the references together. Like it's going to make sure that you it's going to try to make it so that you can't really shoot yourself in the foot, but it is something that you have to be really careful with, right? If you, every time you take a reference, for example, to the slice, it makes a copy of the slice without copying the underlying byte buffers, you're still taking an extra allocation, right? So there's a bunch of optimizations that are there to make sure that there's as few allocations as possible, which make it difficult to use, but that's the cost of performance, I think, at this point.
Thank you very much.
Yeah. There's a question here.
Hi, nice presentation. Is this an issue only in Go? How about Java and Python, other gRPC implementations? Or do you plan to address them in other?
So I know that Java did a bunch of work, I think a year ago or something like that, where they made a lot of improvements for performance, and I don't know the details, but they did something similar wherein they were ref counting the buffers and ensuring that copies are limited. With C++, I'm pretty sure like performance has been like very critical for them from very early on. So I don't know what like frameworks or like what utilities they have, but I'm pretty sure they have something in there. This talk is very specific about the problems that we had in Go and the solutions that we have for them now.
Okay, I have a couple of other questions, but I'll see if anyone else want to ask any questions. Okay, so I have a very fundamental question on the network level. So before you guys write into the network buffer, before it leaves over the network, on the wire, how does it actually ensure that the network is actually live? Because the problem that we are facing right now is between the client and the server, we have a proxy, Nginx, and sometimes it doesn't know if the underlying network is actually broken.
Mm-hmm.
It wouldn't tell the client immediately that the connection is broken, so it actually holds on to it. So there are a bunch of settings that goes on the Nginx to relay that information that the underlying connection is broken to the server. So I was wondering what controls we have or options we have in place before we can write into the network buffer that the underlying connection is actually broken and that there is no point in shooting in the dark.
So gRPC supports keep alives. So you can configure those keep alive parameters on your client and the server, and that will help you detect broken connections.
Yeah, so if I may, so the keep alive pings are actually not carried forward to server.
Mm-hmm.
We have a problem with the selection. I think it's probably a limitation on the proxy selection, Nginx fundamentally.
I see.
So I'm not sure what others, I haven't actually tried them like Envoy or any other proxies. So we have a fundamental problem with that too.
Okay, looks like we're running out of time, but we can chat offline and follow up. Any other questions?
Thanks. This is probably the biggest, most important feature from gRPC, like that I've wanted in a super long time. So thank you for that work. Have you considered, you were mentioning kind of like marshalling and unmarshalling, taking on any of the kind of work that the VT protobuf folks have done in order to basically help with allocations on the serialization front?
I think I can probably speak to that a little bit. We've been having a couple conversations with them on the GitHub issues, et cetera. They're probably the best placed to, so the way that it works today, unfortunately, the proto API, which is below the gRPC APIs, takes in one contiguous byte slice. So the way that the current encoding works is that it actually will create a buffer of the corresponding size, fully materialize the buffer slice, completely getting rid of the advantage of it of having it at all, pass it to the proto encoder, and then do the reverse, right? The VT proto team is probably the best place to start making progress in that direction, and so I know that they have some initial sort of thoughts on how it should work, but yeah, we're keeping them in the loop for sure.
Right. Yeah, thank you everyone for coming. We're losing the room, I guess, and thanks once again to Paul. Thank you all.